Hello and welcome to lecture 15, and in this lecture I'm going to be covering Amazon's DynamoDB. So I'm going to start with an introduction, tell you a little bit about how Amazon DB sort of came about and sort of performance, this kind of stuff. Then I'm going to go into the architecture of DynamoDB, things like tables, items, indexes, that kind of thing. And then I'm going to explain with quite a few examples how you can work with JavaScript and DynamoDB, or TypeScript as well. Okay, so a little bit of an introduction. So DynamoDB is a NoSQL database, so it's not big on maintaining extra tons and tons of consistency between the data and different contained within different items. It's a little bit different from other NoSQL databases such as Mongo, because the internal architecture of DynamoDB is to some extent exposed. So it's this sort of slightly strange combination of a database and a distributed hash table. So if you use, say, MongoDB, then you're presented with a document, database, based on JSON and all this kind of stuff. Whereas DynamoDB is sort of super optimized for being really fast and really scalable. But the price you pay for that is that you actually understand a little bit about how the kind of keys are organized and how the sort of internal architecture actually works. So that's why it sort of is presented to the user as this combination of a database and a distributed hash table. It's developed to support Amazon's e-commerce operations. So I think they had some kind of delays, crashes, or whatever, some Black Friday, something like that. So then they built Amazon DynamoDB in order to be able to handle enormous amounts of traffic and to be very scalable. So I haven't looked into the figures of this, but I'll bet you some substantial proportion of Amazon's e-commerce operation is actually running on DynamoDB. And Amazon S3, which I introduced in the lecture on Amazon, is also apparently running on DynamoDB behind the scenes. So Amazon's using it for e-commerce, and then apparently another 100,000 AWS customers are using DynamoDB. And what I've seen in a lot of the demo of Amazon technologies, or in the sort of technology, technology days on Amazon event, whatever, a lot of the Amazon engineers, see DynamoDB as the kind of go-to place to sort of knock up a database and do stuff with it. So it's used a lot by Amazon engineers as well. So Amazon DynamoDB is all about performance. It's built to have this kind of raw power and raw scalability, and it does that very successfully. So all of the data is stored on solid-state drives, and it claims virtually unlimited storage and throughput. So if you're going to use up as much data and throughput as an entire Amazon data center, then you're going to start hitting the limits of a DynamoDB. But for anything half sensible, you can regard it as unlimited storage and throughput. So it scales to, 10 trillion requests per day with peaks greater than 20 million requests per second. That's pretty scalable, right? And the general response time with the standard settings is about less than 10 milliseconds, single digit millisecond response times. So, it's pretty fast, yeah? But these response times, shouldn't be misinterpreted, right? So that's the time from when it receives the request to producing the result. That's the less than 10 milliseconds. Obviously, if you're working from a computer from home or something, you've got to wait, 10 milliseconds, whatever it is, for your request to get to the Amazon data center in Ireland. Then there'll be less than 10 milliseconds response time, and then there'll be maybe another 10 milliseconds, whatever it is, to get back from Ireland data center back to your computer, yeah? So this is less of an issue when you're running in the cloud, because if you're running in the cloud, then your cloud code has to talk to the database, and obviously they're running in the same server potentially, or same data server farm, so they're going to have a lot less latency than you would if you're working, if it's a communication between your company computer and a computer running in the cloud. What you can also do with DynamoDB is add on this DynamoDB accelerator called DAX, and that will give you read times that take microseconds, so really, really fast. And what DAX does is it puts instead of having solid state drives, it sort of copies the data into memory like Varnish does, and then it can reply with the data extremely fast. So in terms of security and reliability, as I mentioned a couple of lectures back in the lecture on AWS, you have these different geographic regions for EWS. So you've got Ireland, East Virginia, I think it's a London region now. And within each region, you have several data centers on physically separate locations. So these are called the availability zones. So suppose this is the Ireland region. There'll be 3 availability zones within that. I think it's roughly that. And then these are physically separate locations connected with extremely high-speed links, so that you have, if you upload your data into a region, it can then, DynamoDB data at any rate is copied between these availability zones. So if, for example, there's an enormous flood and it washes away, this data center here, then you've still got your data, replicated across these 2 data centers here. So it's sort of pretty secure and pretty reliable. Yep, so that's the availability zones. It's got built-in encryption, which is obviously important when dealing with the cloud and some of the issues that, again, I mentioned previous stuff on the cloud. And you can set it up so that you continuously back your data up, or you can have this sort of backup points. Got restore functionality built into it. And within each region, they claim 99.99% availability. So that's pretty good, right? Most of the time, your database is going to be up and running. And you can configure your table to be global, which can increase the, because then instead, if you can configure it to be global, then your table can be duplicated across regions as well as within across availability zones, and that can give you an extra, extra level of reliability for some super mission critical stuff. But most of the time, 99.99 is pretty good, right? And maybe it's even better than that. Should also mention, because I don't think it's in the slides, that it's a managed database, right? So once you need to figure out the parameters and the pricing and all that kind of stuff, but you don't have to, deal with too many of the configuration settings, and certainly not in terms of when it comes to the scalability stuff. So as with all kind of cloud-based stuff, the pricing, becomes a sort of integral part of it, because you don't just pay, you're not just paying for like a server, right, per month. With DynamoDB, you're paying for reading, writing, and storing data. You're paying for the service here. And you can have 2 price plans, roughly speaking. So you can pay for, on demand, which means whenever you use it, you pay some small amount for, pinging, accessing some data from the data or storing it in the data, in the database. Or you can say, well, I want, 10 reads per second, and then I just want to pay for 10 reads per second. And then you always pay for 10 reads per second. But maybe that price is going to be a little bit cheaper because you're providing predictability to Amazon in terms of, and they're selling you a bulk sale kind of thing, yeah? So you can run a price calculator. So whenever you're doing price calculations, obviously you have to balance the cost of the cloud versus the cost of running it in your own office space with all the, engineers and electricity and servers and all the rest of it. Yeah, so you need to somehow do some kind of balance. I'm guessing it's going to be cheaper running stuff in the cloud, but if you, particularly when it comes to things like DynamoDB, if you've got a lot of data and you configure it badly, then you could end up spending a lot of money. Yeah, so you need to be quite careful when you're using DynamoDB in terms of thinking about how to organize everything. Yeah. So let's just go for a nice. So this is the DynamoDB price calculator. Let's just wait a minute. Let's just knock it down to something sensible to start with. Okay, so let's suppose let's just get that all to 0. Okay, righty-ho. So now we're down to 50p somewhere. Excuse me. Okay, so let's just get it down to nothing. Yeah, why is that still 50p? All right, don't know why it's still 50p. I maybe just refresh it actually, because it should be nothing. Some dodgy bit of JavaScript there. Okay, so let's go to the calculator. Yeah, so now we got nothing. Yeah, so if we had a database of 10 gigs, let's say, I mean that's quite a lot of data, much more than you're going to be using in your projects, but we're still on 0. Yeah, and then we might say provision capacity. Let's say we know we're going to have like 10 reads per second. No, let's not have transactions. Let's have 10 writes per second, for example. Then we're still on 0 here, right? And let's suppose we also want, number of million reads per month. Let's say a million reads per month, million writes per. Oh, sorry, forget about transactions again. About messing around with transactions. Number of reads and writes per month, like 1 million, and then we're on to like 25p, right? It's pretty cheap, yeah. Now, if we increase the amount of data in the database, each item's still the same data set, but we're reading and writing larger items. Then that increases the monthly bill, and obviously if we've got like masses of customers, right, 100 gig, that's a lot of data. Then we're getting up to like 35 quid or something like that. Yeah, and we might want to say, well, actually, maybe got a lot of customers got 100 reads and writes per second, and then we're getting up to like $50, something like that. So So you can see that it's not expensive, right? We're storing 100 gigs, and we're doing 100 reads and writes per second and 1 million on reads and writes and on-demand capacity. So, let's face it, it's pretty cheap, right? To store all that data without any management issues. But obviously, you need to keep an eye on your pricing and potentially, write your database code and design your database to minimize the pricing. That's a very important part of using cloud data services. Okay. So yeah, done that. Right, so as I'll come to in the lecture on Lambda, I think it's in a couple of lectures time, something like that, you'll see that DynamoDB can trigger events, which is nice. So you write some data to DynamoDB, then DynamoDB will trigger a Lambda function, which can push the data to a customer or do some more processing on that data or that kind of stuff. So it's very nice integration between DynamoDB and Lambda, and that's probably true of other Amazon databases as well. Okay, so that's the a little bit of a introduction to DynamoDB. Now let's have a little look about how it works under the hood. So the architecture, we've got items, we've got tables, we've got these partition and sort keys, which you really need to understand to make the best of DynamoDB, particularly when it comes to querying. And then we have indexes, which kind of interact with these partition and sort keys in a way that I'll explain. You've got some naming rules, as you expect with any database. I mean, fortunately, it's a lot more flexible and more like, writing Java, I guess, or JavaScript, because you've got case sensitivity, so you can use camel case, this kind of stuff. You've got name length restrictions, and the usual A to Z, capitals, small a to Z, numbers, a few underscores, dashes, and dots. Pretty, not that restrictive, and should be pretty standard stuff, same as most databases probably. The thing that's a little tricky with DynamoDB is it does have a long list of reserved words. So, and you mustn't use any of these reserved words. Let's just maybe actually click on that. So this is a long list of, reserved words. Yeah, you can get away with using them a little bit. It depends, but not really when you're actually querying stuff. So to give you an example, when I created my example database, I'm going to show you later. I used timestamp as one of my primary partition key, yeah, and that sort of made sense. Timestamp, it's a timestamp, right? But then when I started trying to query on that partition key, then it wouldn't let me because it claimed that timestamp was a reserved word because it was a reserved word, yeah. And probably if I'd had an attribute value timestamp or an attribute value, set to one of these other reserved words, then I'm going to run into trouble. So it's better just avoiding all of these reserved words. And if you hit a problem, then you just got to change the table, which is a bit of a pain because it's not easy to change the partition and the sort key. Right, so the items are equivalent to rows in a standard relational database, or in MongoDB, they're equivalent to JSON documents. It's really, think of items in the way that you have documents in MongoDB, because they're pretty much exactly the same, yeah? You've got, JSON format, key value pairs, yeah, and you can have nested structures, so you've got another sort of object, this key, this attribute points to a substructure kind of thing. And each item's less than 400 kilobytes, which is pretty big, so you're unlikely to run across that problem, unless you're doing something very specific. Then these items are gathered together into tables. So these tables, same as relational database tables, same as collections in MongoDB. And while you have a limit on the size of items, you don't have a limit on the number of items per table. You can just put, as many as you can throw at it, and DynamoDB will handle it. That's the beauty of DynamoDB. So now we get into the more, specific and confusing stuff about MongoDB. We have these partition, and sort keys. So we can identify items in two ways. You're kind of used to this already, but it hasn't been as important in the other databases that you've used on my courses. So in MongoDB, for example, each document has a unique identifier associated with it, right? Typically generated by MongoDB itself, yeah? I think there's some way to auto-generate stuff in DynamoDB, but I haven't explored it, yeah? So we can have a unique key, and relational databases the same, right? Each table, you have the primary key, right? So it's not that surprising that we have something similar in DynamoDB. We have what's called a unique partition key. So we can just associate each item with a unique partition key is what it's called. Or we can specify that the item should be identified by a combination of a partition and a sort key. Now you might think, well, does this really matter? I can just create an ID and, you know, who cares? The reason it matters is that any queries on your DynamoDB table are limited to, if they're going to be efficient queries, the partition key and the sort key. So if you want to pull data out that's not the entire data set, you're going to be doing it using these partition keys and sort keys, and you're either going to have to use the ones that you create with the table, or you're going to have to add on indexes that have different partition keys and sort keys that will enable you to pull out different, run different queries on the table. So this is what I meant about the kind of guts of DynamoDB kind of appearing to you as a user of DynamoDB, in the sense that this partition sort key stuff is used for the distribution of data in the internal, you know, the code that's running this stuff. But you have to work with it. You can't just sort of use a nice interface that ignores the implementation details. So we have the partition key, or the combination of partition and sort key, and this key attribute must only hold a single value. You can't have a key attribute, you know, going to my examples, I couldn't have address as my partition key or sort key because it's complex, it contains other attributes. It has to be like a string, a number, or a binary, right? But, I mean, that's kind of sensible. So it's worth just thinking, bearing it in mind very briefly how this stuff is working and why it's so efficient and why DynamoDB is so good, but also a little tricky to work with, yeah? So how DynamoDB works, very roughly, this is some diagram off Amazon. We have this is the partition key here, which is just a string called dog. So in order to store this item here, what it does is generates a hash of the partition key, dog in this case, and uses the hash to allocate to choose where to store this item here. So because of the hash comes out some value, whatever, it sticks it in this partition here. And then if we did a hash of bird, it would bung it in here, or a hash of cat would end up here. And if we did a hash of fish, it would end up here. And obviously that enables them to store your item across a large number of different SSD drives if it's a large table. Now partition and sort key, it does a combination of two hashes. Yeah, so it does one hash on dog, the partition key, which is still the partition key here, which will take it to here, and then do another hash or operation to put in order to store to uniquely identify the record as well. Yeah, so it hashes dog and Fido together, so to speak. Does one hash to put it in here, second hash to put it in a place in here, and then we can put in, and that enables us to specify a unique location to store this document. If we want to get this document back, we say we want to find the document that's got animal type dog and name Fido. We just run these two hashes, and it'll take us to this exact point within this memory location in this SSD drive or whatever partition corresponds to. Yeah. So it's used to store the data, and then hashes are a very fast way of retrieving the data. We don't have to scan all these records and look for one that matches this. We can just go instantly to this part of the memory or this part of the SSD drive and fish out the data we need. That's the point of this hashing and the point of this partition and sort key stuff, yeah? It'll probably become clear when we do some more examples, yeah? So queries that are efficient queries we'll just be able to specify, some combination of the partition key and sort key, and then go straight to the bit of memory that we need to pull out the exact records that we need. But what if we want to query a different attribute of the data? What if we wanted to get like the, the age of the dog, for example? We want to pull out all the dogs of a specific age, or if we want to pull out all the dogs who have like brown fur or, ginger fur, whatever, yeah? We're going to have different kinds of queries, but that's not supported, right? We can only query efficiently doing this hash stuff on the partition key and the sort key. So the way you get around that is by creating different indexes. We have a different, so DynamoDB will build up different representations of the data, so it can instantly generate the same kinds of hashes and find different parts of, and extract different kinds of data from memory using a query. Yeah, if you don't do setup indexes, it's possible still to get that same bit of data, but only in a very inefficient way. You have to scan all the table and then apply a filter to get just the bits you want. Whereas if you create indexes, you can avoid this whole scanning and filtering business, which is going to cost you money potentially as well. So we create secondary indexes so we can support different types of query on the table. That's the crucial thing that you have to do with Mongo, with Dynamo, which you don't have to do with Mongo. Mongo will let you do all kinds of queries except for the, free text search inside text, without, creating all these secondary indexes, right? There probably is some indexing in Mongo. There's definitely indexing in SQL databases to make the queries more efficient, but you really can't get away without indexing in DynamoDB. So there's two types of index you can create, called the local secondary index and the global secondary index. So in the local secondary index, the partition key is the same as for the index is the same as the partition key for the table. So the local secondary index's partition key is the same as the partition key for the table, but you can specify a different sort key to do different kinds of query. The sort of so that's a limitation. The second limitation is that you can only create local secondary indexes when the table is created, and you're allowed 5 per table, and these don't actually seem that useful to me. More useful ones, I think, are the global secondary index, where you can specify a different partition key and sort key combination and do more sort of sophisticated queries using that global secondary index. And you can add these after the table's been created, and up to 20 per table, which is plenty, right, for most sensible uses of DynamoDB. So final thing I just want to quickly mention, because when you're creating these indexes, you get these options about attribute projection. And the indexes are themselves a big chunk of data that has a representation of the table, yeah? And you can choose, and obviously accessing the index will cost you read time, and it'll cost you storage. You have to pay for storage of your index as well. So depending on your data usages, you might choose to have a small index that only contains the keys, but then maybe you sort of access the keys, and then that, you've got to do 2 reads or whatever to fish out the data, or 2 reads behind the scenes most likely. Or maybe you want a more faster index that has everything in it. So it's effectively a copy of the table organized in a different way, and there's sort of include as some kind of medium thing between the two of these things. You don't really need to worry about these, particularly with the size of data you're going to be working with in your projects. Probably either go for all or keys only. It probably doesn't make any difference. So that's the architecture, and I hope the architecture will become clearer when we go through some examples. So to create tables and indexes in DynamoDB, we can do that on the command line interface, which I'm not going to really cover in this course. Use the console, which is the easiest way, or we could use code. There's like a JavaScript API for creating tables and all this, but I don't think that's kind of a bit tricky and pointless, particularly for us. So I'm going to stick to using the console for the creating tables and indexes. Right, so let's go through an example. So the index I probably won't be able to do completely because it takes a while to create the indexes, but let's just run through a little example. So suppose I want to create a table, yeah? So let's call it people, yeah? Let's create a table to represent people. Now, as I said, this is why you need to understand the partition key and the sort key kind of from the beginning. So what I'm going to do is create a numerical ID for my people. That seems sort of sensible, yeah? And we're going to add a sort key as well. So it's not going to be terribly useful, this sort key, but let's suppose we have email as our sort key, yeah? So we can specify a person. I don't know if we really need a sort key, actually. We'll add a sort key anyway. So this table is kind of a bit rubbish, and you'll see why it's a bit rubbish, but we can kind of fix it with an index. So so let's stick to this ID email thing. We could probably just have if we're being sensible, we'll probably have the ID just to use the email, but let's go with this for the moment, yeah? So it's only an example. So we've got a partition key ID, so it's going to be unique for every person. And then the sort key, we've got email, because it's always going to be, with this index, we're always just going to pull a single person. So that's why the ID is a little bit, not very useful. Anyhow, so at table creation time, we can add a secondary index. So to make it a secondary index, we have to use ID, and we can do a different sort key. Let's say we do phone, yeah? So each person has an email and a phone, and you can see you have to keep an eye on index names because we use them when we're specifying queries using code. Yeah, we don't need to worry about that. So project attributes all, doesn't really matter, it's going to be a tiny table. And then we add the index, and then if we were looking seriously into that, we'd figure out all these parameters. But for the moment, we're not going to worry about it. And encryption, default server-side encryption. So it's all good. You can fiddle with these parameters if you like, but we're just doing a very simple example here. So table creation and index creation does take a while on AWS, so no way around that really. It's very fast when you're adding and using it, but it does take a little while to actually do its thing. Right, there we go. So because we're working with the educate account here, we get these annoying authorization errors which I mentioned before. So now we can go have a little look at the table. So we've got our people table with partition key, email ID, and then primary partition key is ID, primary sort key is email. So let's add a couple of people. So we go to items, create item, so ID, let's call it 1, email d@g.com, and phone number 1234. So that's one person, right? We just have to make up our own IDs here. And then we can have another person here, ID 2, email x@y.com, and phone number 6789, let's say, yeah. So now we got 2 people. And here, I'm going to illustrate this later, but I think probably worth introducing it now. We've got two ways in which we can pull data from this table. We can do a scan. If we do a scan, it just pulls all the data from the table, yeah? Without any, and you can add filtering to, control. So it pulls all the data, and then filtering will limit the data that's actually returned to the user, yeah? Whereas with query, we can look for specific things within the table using the partition key and the sort key. So we have to specify the ID, so in this case 1, so we can just do a query by ID, that's fine. But we've also said that the email, which is the sort key, is going to be unique, so we could, although it's not going to help us much because we already got the record, d@g.com. Okay, so we could search for a combination of the primary of the partition key and the sort key. And also we've got a sort key, email, right, so if I wanted to search by sort key using the 26789. So here I'm using the index, the secondary index I created, which is a combination of the primary partition key and the sort key, with the sort key being the phone. So I can look for 26789, and it's found that other record there. But you might say this is kind of rubbish, right? Because yes, if I know the ID and possibly the phone number, then I can get the record, right? That's useful under some circumstances, being able to go from the ID to the particular record. But what if the person gives me their email address, right? And I want to pull out the record using the email address. Well, I can't do it using DynamoDB as it stands, yeah? To make that work, I need to add an index to it, and I need to index the email address so then I can run searches looking for records that have a particular email address. So probably won't be able to finish this demo because it does take a long time to create indexes. But let's say we want to create a new partition key within this index. So I can use email here. I don't think a sort key is going to do me any good. So let's just create our partition key with email. And it's successfully created index, but this is the annoying IAM stuff that you get with Educate. So I don't think we're going to sit here and wait for this because it does take ages to create, but I will show you it when I next come to do a demo. We'll come back and have a quick look at it because it should have finished creating it. Okay. So turn the architecture. Right. So that's using the console to create our tables. We can manually add them using add item, and you can manually do queries on the console. So as I said to you when we were doing SQL last term, whenever you're trying to do something with your database, it's always a good idea to test it out first using something like Heidi for MySQL or something like the console for DynamoDB. Test your queries out first without the code, without anything, make sure they work, and then run them on your code. You're going to save yourself a lot of hassle with debugging that way. Okay, so in this section, I'm going to talk about how we can use JavaScript to manipulate the data in a DynamoDB table. So assuming we're using the console to create the table and configure the table, but then we want to use JavaScript to change the items in the table. So in your coursework 2, you're going to use TypeScript compiled to JavaScript to upload web service data to DynamoDB. So that's kind of what I'm going to show you here. And you're also going to be using JavaScript to interact with DynamoDB in the cloud. So you're going to be writing Lambda functions that pull out data from DynamoDB, do something with it, maybe put it back into a different table in DynamoDB and all that kind of stuff, yeah? So we're going to be doing a fair amount in this coursework of interaction between JavaScript and DynamoDB. Now, I think I mentioned this in the TypeScript lecture, but to make TypeScript work with Node, you need to install this node.d.typescript. I think it's like the types or something for Node. So it's very simple, just npm install type/node save dev. Save dev means that it's not going to be uploaded when you deploy it. Otherwise, you don't recognize, TypeScript doesn't recognize require, which is kind of annoying. Well, it means you can't use it, right? Okay, and you also obviously need to install the Amazon SDK, yeah? So you just npm install AWS SDK. So once our development environment, and obviously development environment also includes making sure you've got the .aws folder with your credentials file inside it. Otherwise, none of this code is going to run, yeah? Okay, so for demonstration purposes, I created a very basic table to hold the price data for different cryptocurrencies. And each of the items in the table has the following information. So we've got the price timestamp, which is just the number in Unix time. So most of you have probably come across Unix time. It's the number of milliseconds since 1/1/1970. Okay, it's a big number. Just quickly look at an example of it. If we go to my crypto table, wait a minute, it says index created. All right, all right, we'll come back to that. So if you just go to, so these numbers here, the price timestamps, are the number of milliseconds since 1970, yeah? So it's just a way in which you can represent an exact date with millisecond precision, an exact point in time with a millisecond precision using a single number, yeah? So Unix time is very sort of commonly used, and actually JavaScript uses it as its internal representation for the date class. So this is our partition key, primary partition key, price timestamp, which is a timestamp for the cryptocurrency prices. And then we got the currency, you know, Bitcoin, Ethereum, so on and so forth, and then the price. So you can see what we're doing here. We've got the prices coming in for each of the currencies, and we're giving them a timestamp when that price is valid, the name of the currency, and the actual price. So it's pretty easy, yeah? And I wrote a little bit of code that fills this table with random data. So I got the current prices, added a 10% fluctuation for each of the currencies, and just dumped a load of data in so I could use it as an example. So I included this in the example code for this week, but I'm not going to go into the details here yet. So if we have a little look at the table here, this is the table. So we've got each item here. So if we go on here, we've got the currency, which is Bitcoin in this case. This is the price of Bitcoin. And this is the time, you know, in exact date time combination in this Unix timestamp business when Bitcoin had that particular exchange rate, I think with a US dollar, something like that. Okay, so that's the table. I think, didn't I mention that's the table. Okay, then, well, since we're going back to this, at the risk of a mild amount of confusion, let's just finish off this example here. So if we refresh this thing, you remember I added an email index. So now with the email index, if I do a query, I can now search with by email. Yeah, so if I want to search for d at g.com, because I've created an index which is now active, I can now do searches by email. Yeah, so I added that email index, which now supports more sophisticated queries. Okay, so for my crypto table, I also need an index. So I've got the main index, which has the primary partition key being the price timestamp, and then the primary sort key being the currency. So that will enable me to search for all of the records that have a particular timestamp, or all of the records that have a timestamp that have a particular combination of a currency and a price timestamp. So I can, even though I've got a sort key specified, I can just get all of the records with a timestamp, but then I can also get a unique record, which is a combination of the price timestamp and the currency. But this wasn't good enough for what I needed to do, because, like, suppose I want to do a graph of Bitcoin prices, yeah? This won't allow me to do it. I can only pull, unless I just pull all the data, right? This is a bit useless if I want to just do like Bitcoin prices since yesterday, for example. So to support more sophisticated querying, I created a global secondary index. I called this is the name of the index, which we'll use when we run queries on the database. And here the partition key is the currency, and the sort key is the price timestamp. So this index will let me pull all of the currency, all the items for a particular currency. So I can get all of the Bitcoin items or all of the Ethereum items and all that. I can only do that using the global secondary index. I can't do that here. So that's why I had to create this secondary index. Okay, so I've already shown you a little bit about this, but let's go back to it because got a little bit distracted by the people table. So here's my crypto data. So here's the index that I created. I also added a price index to allow me to sort of do some filtering, but to do some querying by price. So there's this is will let me select a particular currency, and this will let me select particular records that have a particular price. So here are the items. I think we kind of went through that already, right? So it's increasing timestamps with the prices of each of the 4 currencies at each of the timestamps. And if you want details of the table, we've got it here. And I think that's about it. Yeah, I think that's pretty clear. So that's my demo table. That's what we're going to be manipulating using the code that I'm going to show you. So we change data in DynamoDB using these key methods, which, as you can see, are kind of similar to HTTP RESTful stuff with a couple of extra bits. Yeah. So we've got put, get, update, and delete, which is pretty much the same. So put is a bit like post, right? Update a bit like gone hazy here, but put maybe. And then we've obviously got scan, which is new, and query, which is new. Yeah, and deletes standard HTTP stuff. So puts something in the table. Get returns a single unique data item. Query lets us query the table in a way that's a bit similar to MongoDB queries and a bit similar to standard SQL, but it's quite particular in the way it does it, and I'll explain how it works. And then we have scan. Again, I'll explain some more detail, but scan just returns, scan will just scan the entire table. There's no sophistication in scan. It just goes through the entire table, and then if you want to, you can then apply filters to the return data. So with scan, you're going to pay to access every single item in the table, whereas with query, you're only going to pay to pull out the items that match the query. So query is much more efficient than scan, and you only use scan if you just want to pull everything. That's the usual use case. Then we have update that lets us change the data in the database, which is obviously useful, and delete as well. Yeah. So how this works with code in JavaScript is you've got the method, one of these things, put, get, query, etc. The first argument of each method is a set of JSON formatted parameters that control what you do to the data in the database. So you've got the method that determines the action you're engaged in, and then the parameters that control how you do that particular action. Yeah. So this is a little example of the parameters. And then the second argument of each of these methods is a callback function. And that callback, because this is all asynchronous, right? So what happens is it'll go off, do whatever it does to the database, and then it will call the callback function, which will handle errors or do something useful with the data. And you can always wrap all of this in a promise if you need to sequence calls to the database. So let's run through some examples, and I think you'll see that's pretty clear and pretty easy and pretty simple. Yeah. So let's go for put. So that adds a single data item to the table, and since it's a single data item, we need to specify the partition key and the sort key if that's what determines a unique item in the table, or if the table just has a partition key, then you need to specify just the partition key. So this is the sort of code for doing that. So most of this code is standard for all the methods. But let's just run through it once. Yeah. So at the top of this, I've got obviously I need to be able to use the AWS SDK, and then I need to configure AWS to be able to use the region that I want to work in. So here I'm using this is for my free tier account. I actually have slightly different code for the educate account, but here I'm using the Ireland, right, EU West 1. I need to specify the endpoint that the JavaScript will talk to manipulate data in the database. So this is like the endpoint for Ireland. Then for all of the examples, I'm using the document client. You can work with DynamoDB's API directly. It's got its own API. The document client just makes things a little bit smoother and easier, so I prefer using the document client. So all of the methods have a set of parameters, okay? And this is the put parameters here. So obviously we're going to specify the table name, which is crypto data. And then here we've got, I'm putting an item, so I want a unique timestamp. So I'm just getting the latest timestamp. So this is my price timestamp. The currency here is Bitcoin, and the price is there. So you can see I'm specifying the item that I want to put, and then I'm specifying the partition key and the sort key in the item here. And then here's the actual method. So here we got the method here, put, and the parameters that I created here go in here. And then we got the callback method here, specified with lambda, and then, you know, it just does the error handling or says, you know, it's all work fine, yeah? So it's pretty easy. They all work the same. You have the method, parameters, and the callback. So let's have a little demo. So let's go for put. Now I may have a slight issue. I may have to refresh my keys because I think they're about to expire. But yeah, we'll see how we go with that. Yeah. Not session time also. Yeah. Okay. All right. So let me just fix my keys. I don't really care if you see these because it's got a unique session key on it anyway. So if you watch this video in the next hour, you'll be able to access my account, but after that you won't, so I'm not super stressed about that. Right, so let's fix the keys first, because if you're working with Educate, obviously it's got it's got the session key business. No, I can't see this. Come on. That's what I want to see, but it's gone off. Right, okay. Slightly annoying. Okay, so let's bung in my new credentials with my session key. Actually, it looks the same to me, but we'll try it. We may have an issue with the key here, yeah. But let's just go for put. So the put demo, exactly what I showed you, right? We specify the parameters. This is what we put in, and you know, if it works, it works. If it doesn't, we'll have to fix the key somehow. So let's do my right. So when we're running stuff in WebStorm, probably different environment. Obviously, you can't run the TypeScript. But when I save the TypeScript, it's compiling it to this JavaScript here, and it's the JavaScript that we actually have to run. Yeah, so let's run it and see if my session key is still working. Yeah. Oh yeah, it's worked. Okay, so here we have the currency being out. This is just outputting. This is what's outputting here. The parameters that were specified. You know, just to echo it back to the user shows it's worked. Yeah. Now, one thing I need to explain here. In WebStorm, it might be true in other environments. You know, not a TypeScript guru. I had an issue that any variables I created here could potentially conflict with any variables in any of the other files. Yeah, so in standard JavaScript, you don't get name conflicts between files. But with TypeScript, I was having this issue. So what you can do is you can wrap all of your code in a namespace, and that means that all of these variables will be local to this particular file, and that just makes it easier. Then I could create a put demo and like a scan demo and all this kind of stuff, without having to call this date 1 and this one date 2 and all this kind of stuff. Yeah, so that's what the namespace is about. I think the rest is pretty clear about the code, and that seems to be working nicely. Okay, so that's put. We put stuff in the table, and now we've got get, yeah, which will retrieve a unique data item. Yeah, so here I've got an item. So to get a unique item, I have to specify the key that will uniquely specify that item. So here I'm saying a key is a combination of a price timestamp and a currency, because I'm using a partition key and a sort key here, and all the rest of it's the same. So the important stuff here is we change the parameters, in this case specifying a key, and we use the get method, and all the other code's exactly the same. So let's have a little look at a get. Okay, so this is my get. That's exactly the same. Oh yeah, so in the example code I'll give you, you can either configure it. I've got 2 configuration options, right? One for the Ireland option and one for the Educate account option. Okay, so again, let's run the get example code. And there we have it. Yeah, we wanted this price timestamp, this currency, and it's returned Litecoin and the price, Litecoin and the price, and that kind of stuff. Yeah. So get's pretty easy, pretty straightforward. And then we got queries. Queries are where things get a little bit messy, because you have to really understand what's going on with partition keys and sort keys. Yeah. And the sort of slightly, what might seem a little quirky about queries to begin with, is that they separate the logic of the query from the data from the query, and I've got a sort of vague memory of how, you know, I used this stuff years ago, that in some, you know, in some environments, you know, this is quite common practice, so it's not as strange as you might think at first. Yeah, but I'll give you an example to make clear what that means. And then we can perform equality tests. You know, we might want to query all of the records that are in the last week, or we might want to query all the records that have a price greater than a certain value, all this kind of stuff. So we're going to perform comparison tests on the sort keys. And the usual greater than, equal, less than, whatever, all this kind of stuff, yeah? And we can query on the table index, i.e. the partition key and sort key we specified when we created the table, or we can query on one of our indexes that set up the partition keys and sort keys differently so we can pull out different kinds of data. But the query is always relative to a partition key and sort keys combination. So let's go through a little example. So here's our parameters for our query. Yeah? So we've got this key condition expression. This is the logic of the query. So here I want to find a record that has a specific timestamp. Remember, we're not getting a unique item here. We might get a load of items. We just don't know. So here I'm saying I want the price stamp to equal, and then here's what I meant about separating the logic of the query from the data. So what we have is here we have the expression attribute values, which have the data for the query. And then these are given like a key, in this case TS. It has to have this colon so that it can pull it out easily, I suppose. So we create a variable. It's kind of like a variable preceded by this colon. In this case, I've called it TS. And then within expression attribute values, you have to have TS present, pointing to, you know, the value that we want. Yeah, it would be much easier, of course, if we just do price timestamp equals that number. But using this, you know, methodology or this, programming approach, shall we say, we have to do it this way. Yeah. So price timestamp has to point to, if you want to put data in here, it has to point to this, and I could have called this anything. I could have called this, David 2 or something. Yeah, as long as what I called it here matched what it was here. There's nothing, you know, magical about TS. It's just my short abbreviation for timestamp. Yeah. So it's just like a local variable, effectively, which I create here and has to match something here. Okay, so this query will get all the price timestamps equal to that timestamp value, and obviously we have to use the query method here. Okay, so let's do. I think I'll do the query demos as we go. Yeah. So here's my query demos. So with the query, I haven't bothered creating separate files for everything because all that's changing is the parameters. So I've created different parameters to do different kinds of queries. So this is the query that I just talked through, I think with a different timestamp because I changed the data slightly. So let's run this query, and it's still working. Okay, so there we have. So it's pulled all the ones that have this particular timestamp 86868666, 4 items, which makes sense. Yeah. So that's a very basic query, and the nice thing you see with queries is with get I have to specify the price timestamp and the currency, so I'm only getting one item. In this case, I'm getting all of the currencies that match that particular price timestamp. So now we're getting something that's a bit more useful here, yeah? So then I could, and you know, if I, and I think I can, yeah, I could pull out different combinations of that, as we'll see with different queries. Okay, so where's my, that's my partition key, covered that. Okay. Now we might want to run different kinds of queries on our database, yeah? It's useful being able to pull out all the prices for a particular point in time. That's good, right? Not bad. But maybe I want to pull out all the prices for a particular currency, yeah? That'd also be very useful, yeah? So in the standard crypto data, the primary partition key is the price timestamp and my sort key is currency. But as I explained in the case of the person table, I always have to specify the price timestamp if I'm querying just the standard table. Yeah, I can optionally specify the currency or not, but the price timestamp always have to be present. But what if I want to pull out all of the prices, all of the currencies, all of the Bitcoin prices, regardless of the timestamp? Yeah. To do this, I need to create a global secondary index, which I explained in the previous section, and I need to specify the name of that index in the query. So in this case, I've got an index called currency price timestamp index. Now, if you can't remember what they're called, let's find that here. If we go to indexes, right, we've got the names of the indexes here. So if you can't remember what they're called, then the index is specified there. And then for the query itself, I can then, if I'm using that index, I can then specify that the currency should be a particular currency. So again, we're using this sort of distinction between the logic and the data of the query. So the currency is equal to Bitcoin. So by using the index, I can then query by the particular currency. Okay, so let's have a little run that. So that's the first example, right? So let's run the next example. So I want all the items of a particular currency. That's what we're going to do here. If we run that. I can't remember where we go. Yeah, 11, right? Because there's 11 price points for Bitcoin. So you can see all these records of Bitcoin giving the different prices at different times. Yeah. And incidentally, we could have run the same query in the console if you're not really If you're struggling to understand this stuff, then just run it in the console and have a go, yeah? So here we've got the currency price timestamp, so I can specify, Tron, for example, and run a query on Tron, and it'll give me all the records that have Tron, So that's my global secondary index. Great. And then we can also apply filters to the query. Now, filters are to be used with care because you're paying to access all of the items that match the query, and then you're throwing away some of the items because they don't match the filter. So it's not necessarily a very efficient way of doing things using filters, but it does let you work with attributes that are not indexed. So that's the advantage, but obviously the disadvantage is that it's going to take more time because you're accessing more data, and you're going to pay more because you're accessing more data as well, yeah? So everything else is the same, but in this case I want to apply a filter such that the price is greater than P. Now price here in this index is not indexed, I don't think, but I can still apply a filter on that particular attribute, but that, as I said, is not necessarily going to be very efficient. So let's do filters. Let me just see actually. I think I did have a price currency index. Partition key, price, sort key, currency, but I think the filter's working on a different index. Let's just check that actually. So let's go for my filtering. So that's that one. Oh yeah, okay. So let's just do this one first, and then while we're thinking about that. So here we've got the index name currency price timestamp, and then we're applying a filter such that the price is greater than a particular price. Yeah. So just save that, run it. And so here all the prices are greater than a particular value. So I think pretty sure, yeah. So price is not, exactly, yeah. So this index is the currency, contains the currency as the partition key, and price timestamp as the sort key, right? Price doesn't feature in this index at all, but I can still filter by price. I can see it'll look for the attribute price and return the items where the price is greater than 3,800. Yeah. So I'm getting here all of the Bitcoin records whose price is greater than 3,800, and that's what's working here. Yeah. Oh yeah. So I'll just show you the other query, the one that I commented when I didn't come to. So this is just a little example I haven't covered in the slides, but it's worth just mentioning here. So in this case, I'm still using the currency price timestamp thing here, but I can then apply, some query logic on the price timestamp as well, yeah? So here I'm looking for currency, specific currency, Bitcoin, but I'm also looking for a price timestamp that's greater than a particular value. So under many circumstances, suppose you're plotting a graph of Bitcoin prices on your web page. You might have a web service that pushes the data to the web page, but you obviously are not going to necessarily want a million records going back to the dawn of time or whatever. Maybe you just want the most recent records from your database. So maybe you want to get timestamp greater than a certain value, for example. That would be one way of achieving that aim. Yeah. So we save it and run it, and then we got the timestamp greater than whatever that is. Yeah. Okay. All right, now we can do, we just done that one, right? The price filtering, and then this is projection expression. So last kind of query thing I want to cover is projection expression. And that's, in this case, we're saying we're going to pull all these records from table. The records are these items, right? Containing a bunch of key value pairs. And projection expression allows us to throw away some of these attributes to reduce the data size, basically. So if we've got big items, lots of data in our items, but we only want to return a small amount to the user as quickly as possible. So to reduce bandwidth and save passing stuff around, make everything clearer maybe, we might want to throw away. We might only want to retrieve some of the attributes from the table. And so what we have here is a projection expression. So in this case, we're saying we only want the price attributes in the items, yeah, rather than all of the data, which is what we got before. So let's run a quick demo of that. So here we got it. So I must have a duplicate here. Okay, so here same stuff, right? We're getting currency Bitcoin, but we only want to return price. Yeah, that's what this is doing. So now if we run this, and look what we get back. See, we're getting just the prices here, yeah? We're not getting anything else apart from price. So the only attribute that's returned here is price, because that's what I've specified I want to return. That's what projection expression does. Okay, so next thing I want to mention is scan. So that's querying. And as I explained, to query you need to understand, partition keys and sort keys, and it's not that difficult once you put a small amount of effort into that. So next I want to cover scan, and whenever you run a scan, it's going to access every single item in the table. Now, if you've got a small table, you're not going to care, yeah? But if you've got a table with, a billion items, yeah? Firstly, it's going to take a lot of time, and secondly, it's going to cost you money to access every single one of those items. So you can do a very crude form of querying where you scan and then apply filters, but that's not going to be very efficient, and you should avoid that wherever possible. So scanning, very easy in the basic way. If we just say we've got a table here, crypto data, we want to scan it, that just means pull all the data from crypto data. We can also do a scan with filters. In this case, you have a filter expression, price greater than price. So in this case, it's going to scan the table, put all the data, and then it's going to chuck away the records where the price is less than price and just return the ones where the price is more than price, yeah? So I think we can, do a little demo scan. So standard scan, which is here somewhere or other. So this is just the simple scan where it's pulling everything from the table. So let's just run that. Okay, so that's, and you see it's just, not even very pretty. So that's everything in the table. Yeah, so if count 41 means that's the number of items it's accessed. Sorry, that's the number of items it's accessed. That's the number of items it's returned. And then if we run it with a filter, which is going to throw away all of the items whose price is less than 1. And we run the scan again. Don't know why it's taking so long. Maybe I've got network problems. It's either network problems or session key problems. Let's just check let's just refresh this, yeah. It's a problem you might have, so, yeah, okay. So now, as I said, copying these isn't going to help you very much, so I'm not going to be totally paranoid about this. So let's just bung in, probably these are new session keys. Yeah, new session keys. So this is likely to be the problem, because I've been working on this today, and the session key is probably expired. So let's just go back to here and stop this, rerun it, yeah. Yeah, it's run. Yeah, so if you hit this problem, you've been doing this for 3 hours, it's going to stop working. But anyway, it wasn't hard to fix. So in this case, we've scanned, so we've accessed 41 items, but we've only returned 31 because we filtered out the ones with the price less than 1. So as I said, scan's less efficient than other DynamoDB operations. So query can be mind-blowingly efficient and quick. Scan is not necessarily, yeah? Because it scans the whole table or secondary index and removes the values you don't want. And obviously you're paying for every single time you touch that data in some way. So you want to touch that data as little as possible, so use queries and indexes whenever possible. Because query indexes at least only just cost you storage, which is generally pretty cheap, whereas scanning is accessing stuff, and that's generally more expensive. And query is going to give you better performance as well, unless you've got a tiny amount of data, or you need all the data anyway. Right, so update is kind of the reverse of get. It specifies an item and updates it using the key, and you have an update expression saying what you want to do, basically. So here we have a key, which picks out the item we want to change. And then we have the logic of the query, standard SQL stuff, right? We have set price equal to price. And here, the price here is, 1,000. So this is going to update a Bitcoin thing that has a timestamp, like that, something like that. And let's just do a little demo of updates. So there we go. Might have to change that. Let's just check, because I've been practicing stuff. And yeah, it's expired my database as well. Ugh, come on, right, so I need to re-access the console. Just 1 second. So this session business, another irritation about the educate account, right? But it's not such a big deal. Right, so here we are, back in our tables and crypto data. So let's just find, see if we've got any. Oh yeah, I created a price index. That's what I wanted to. So this is a price. So if we query the price index, we can find all the items that have 1,000 things, whatever. And currently there's no records here. So if I find, actually, let's just scan actually. Right, let's just get an item. So let's get this item here and update it, yeah. So if we get this price timestamp here, just to show you it's working. So we'll put the price timestamp there, because I probably updated that one already or deleted it or something. And I'll actually put that into delete to make sure that's going to work, because I think I deleted that one already. Okay, so this is update, right? Okay, so what we should be doing, we've got a price timestamp that, currency Bitcoin, I'm going to update it to 1,000, yeah? So let's just go back to the table, and then we can do our query again, right? So currently I've got no records that have a price equal to 1,000, and then if we run our updates, then bit of luck, it'll successfully update. Yep, it reckons it's been successful, and then we'll run the query again, and we can see we've changed, this record to equal the price of 1,000. Yeah. And delete, as you can guess, is very straightforward as well. Deletes a single item, so specify the method delete, and then we've got the key which uniquely picks out the item we want to delete. So not complicated. Let's just demo the delete. So here's my delete, specifying the item. So I want to delete for that timestamp with the currency. Actually, I'm going to currency Bitcoin, I think, because I think we just changed that, right? Okay, so currently we have, if we do a search for index on the price timestamp on that, so that's the timestamp. Search, these are all the records that have that particular timestamp. We're going to try and delete this Bitcoin record. So we're going to delete one that has the price timestamp that and the currency Bitcoin, yeah? So if we save that and then run it, then it claims that we successfully deleted the item. We rerun the query, and we can see that the records disappeared there. Yeah? Okay, so just to wrap this all up, DynamoDB is great. Yeah, it's super scalable. I mean, it's a tremendous piece of technology. Yeah, you can just chuck stuff at it, and it will scale up to unimaginable limits. You're never going to run out of data or data storage or throughput with something like this. Yeah, and it's pretty easy to get started with. Yeah, and for coursework too, it's just the perfect solution really, because once you've set up the indexes appropriately, you can just chuck all your data in there and pull it out extremely quickly. So it's fast, it's scalable. But it has this quirky stuff about the partition key and the sort key and setting up the indexes, and in many cases it's just not going to be the best choice for your solution, right? There are if you need something that's going to scale up to huge amounts of data, if you're doing some kind of Internet of Things, working for Nest, hoovering up every single bit of data from half the households of Britain, DynamoDB is probably a good choice for that. Yeah. If you're running a small e-commerce website with customers and all that, it'll do the job, but it might not be the best choice. And there'll be lots and lots of other situations in which DynamoDB is not an ideal choice. It's got limited querying ability without these indexing business, and scans really expensive on a big table. If you've got a table with billions of records, you're going to pay serious money to keep scanning it. Yeah, and you'd be a fool to do that. Yeah. As I explained at the beginning, yes, it's fast. It's less than 10 milliseconds from the receipt of the query to to producing the result, but that doesn't take into account network latency. Yeah, so if you're running a local database, you're going to get faster access times than if you have to send your query with a 10 millisecond travel time to Ireland. The 10 milliseconds to run the query. 10 milliseconds back, that's maybe 30 milliseconds. Not a huge amount, but if you're running MySQL locally, it's going to go more quickly probably. But obviously, if you're running MySQL locally, you've got all the hassles of the server room, all this kind of stuff, and then at some point you've got major hassles of trying to scale up your database, as your users increase. DynamoDB is not going to have those problems. And the latency issue is not really an issue if you're running code in the cloud, because then all your Lambda function running somewhere in the cloud somewhere or other then talks to DynamoDB on the extremely fast connections they have within the data center, and then pulls out some data and then sends it back. So the latency only applies in terms of communications from the client to the cloud. Code that's running in the cloud can access DynamoDB much faster. So there are, I came across, several articles critical of DynamoDB. And I think what some people have found, at least, it's easy to get started. I've shown you how to get started, right? But it's challenging to get a good design. You've got to really rethink how you handle data and databases in order to make DynamoDB work for you in a good way. There's this kind of hotkey issue. So you might set the capacity for the whole table, but you're only pulling out like 3 records a lot, and then you can't pull those out to, I'm not even clear what the hotkey issue is, but it's a debated issue within DynamoDB users. And obviously you're going to have this problem whatever you do, but if you've got a petabyte of data in DynamoDB and then you're trying to move it to somewhere else, that's going to be a complete nightmare. But that's true with any petabyte of data, really. So if you're getting serious about DynamoDB, have a little look at the best practices. It'd be a good idea, because when if you work in a company trying to implement a solution, figure out if DynamoDB will do the job, and have a little look through the best practices, which will tell you how to make it do that job in the best possible way. So, of course, there's many alternatives. There's, standard relational databases. For this piece of coursework 2, you're welcome to use DocumentDB if you prefer. I wouldn't recommend it. I think DynamoDB is a better choice here. But if you're super comfortable with MongoDB and want to use DocumentDB, which is basically an AWS version of MongoDB, where you've got the usual, I presume the usual find and this kind of stuff, then feel free to use DocumentDB. It's probably a bit slower, probably less scalable, but I'm not going to stop you. You're also welcome to use another cloud database, but obviously you're not allowed to use I should have been more clear about that. You're not allowed to use a relational database in the cloud. No SQL, what do they got? Elastic SQL, what do they got? It has to be a no SQL database, really. I think that's the most sensible choice here, because I'm trying to teach you stuff that will scale, Another thing you can't use is something that doesn't have internal structure. So yes, you could bung it all into S3, into a bucket, but it'd be you wouldn't be able to pull out the stuff you need to do the querying you need. If you wanted all the records that were greater than a certain timestamp, then if it's just in S3, that's going to be really difficult. You're going to have to do an awful lot of data processing and be a bit ridiculous. So I think DynamoDB is a really good choice for coursework 2. But if you want to use something similar in a different cloud provider, probably not recommended because you've got the event issue. You probably have to stick with AWS if you're using AWS for your Lambda functions. But if you want to use another NoSQL database within the AWS ecosystem, then that's kind of okay. So as usual, got a bunch of resources, got the lectures, video slides, the example code to run through, it's all there. And then some, useful information, a few tutorials, and a couple of articles, saying why DynamoDB is not ideal in some situations, or, some of these are quite critical, but it's worth bearing in mind the critical perspective as well as the positive perspective. Okay, so in this lecture, I've introduced DynamoDB, and in the next lecture, I'm going to show you how we can use all that TypeScript, ECMA script 2015 goodness to download data from web services and then upload it into DynamoDB.